Alright, so looking at our do now, we have a game where we're using a spinner, and it asks us to spin the spinner twice. So in this particular problem, this is what we would call a compound event when we're looking for all of the possible outcomes. So we're listing the sample space here. So for spin 1, all of the outcomes are red, blue, green, and yellow. However, we have a second spin here, so that can make for a lot of different outcomes here. So with the first spin being red, we could also get a second red. So for spin 2, we could get a red, or we could get a blue or a green or a yellow. So what we see here is that for this first spin of a red, there's actually 4 different outcomes. There's red red, there's red blue, there's red green, and there's red yellow. And the same thing with the blue. With the blue, we could then spin a red, blue, green, or yellow. And so following this path, starting with a blue, again there are 4 more new outcomes: a blue then red, a blue then blue, a blue then green, and a blue then yellow. So far our sample space consists of 8 characters, but then again we also have the green and the yellow. So we're going to see the same thing again. Red, blue, green, yellow, red, blue, green, and yellow. And again, we have those links: green, red, green, blue, green, green, and green, yellow, yellow, red, yellow, blue, yellow, green, and yellow, yellow. So this whole piece over here is our sample space. And there are 16, if we count them, possible outcomes in our sample space. This is what we call a compound event, where we have one chance event and then another. So this is something we're going to dig a little bit more into later, and this diagram that I've drawn is what we would call a tree diagram, moving from one event to another, and we're going to explain more about those later as well. So moving forward, this is just the idea that a sample space can have compound chance events. Alright, today's aim, Kipsters will be able to define sample space, and probability, for single and compound events. So we're going to see a few more compound events today, but we're also going to be single events to help us kind of hone in on some of what we already know. So in a previous lesson, we saw that to find the estimate of a probability of an event for a chance experiment, we could divide the number of observed occurrences by the total. So assume that you've seen me with a brown bag, and in this brown bag there are 4 different color cubes, and the cubes are identical except for their color. So when I reach into the bag, I have no idea what I'm pulling out. I am just randomly pulling out a cube, and I am going to pull pull out the cube, and then I am going to replace the cube. So since you don't have this in front of you, if you're watching the video, I've gone ahead and done the experiment ahead of time, and here's what I got each time I pulled it out. And we're going to answer some questions over here. So based on the 20 trials here, so I pulled out 20 times, and those are what we got. What is the probability of choosing a yellow cube? So as I go through and I look at this, I can see that I chose a yellow cube 1, 2, 3, 4, 5 times. So my yellow probability, 5 out of my total observances of 20, and that's going to be 25%. Looking at this, the estimate for the probability of the green, so as I look through, I chose a green 1, 2, 3, 4, 5 times. So once again, this is 5 out of 20, which is 25%. Choosing a red cube, I got 6 out of 20, which is 30%. And I got, for the blue, hopefully that should remain 4 out of 20, or 20%. If there are 40 cubes in the bag, how many of the cubes of each color are in the bag? Explain. So based on our representations here, we should be able to use that. We can use Q is equal to percent times whole, or we can think about using equivalent fractions. So think to yourself, what is the way that you would use to determine, based on our observed probability, how many cubes are in the bag? Go ahead and make an estimate for me for each color. So again, remember one way you can do this, Q is equal to percent times whole, where our whole would be 40 and would be our percent. So for the yellow, this would be 0.25 times 40, and that would give me 10. So 10 for the yellow, or you can think about it in terms of equivalent fractions. 5 out of 20, well, how many out of the total 40 would that be? Multiplied by 2 over 2 would be 10. Going through and doing the calculation for the rest of these, this would also give me 10. This would give me 12, and this would give me 8. This is what I would expect. All right, if I were to randomly draw another 20 cubes, turn and talk with your partner. Do you think I would get the exact same thing, the exact same results next time? Write your answer and explain. So probably not. Between you and your partner, you should have said probably not, and your explanation should be something along the lines of, regardless of what the theoretical probability and what cubes are actually in the bag, it is random chance, and so random chance does have variance in small sample sizes. So we would expect that it would not be perfect, but it probably would be close. So if I went ahead and dumped out the bag, you would find that there are 40 cubes in the bag, and there are 10 yellow, 10 green, 10 red, and 10 blue. Go ahead and find the fraction of each color cube in the bag. So looking at our total, this is going to be 10 out of 40, which is 25%. And they are all the same. So they're all 10 out of 40. Which means they are all 25%. So as we look over here, we've just got a summary of kind of some of the work that we've done already. We see each of these fractions coming out of this is the theoretical probability. So if we were to just look at the bag and know what was in the bag, we would assume that each of those would be represented 25% of the time. So when all of the possible outcomes of an experiment are equally likely, the probability is of each outcome is 1 over the possible outcome. So the probability of drawing a specific green cube would be 1 out of 40. Now, there are multiple green cubes, so all of those would set the collection, and that's why in an event collection of outcomes, when the outcomes are equally likely, the theoretical probability of the event would be the number of favorable outcomes, so we'd be talking about all of the green cubes, or if we were talking about the probability of a green or blue cube, you're talking about all of the green or blue cubes. So for the example here, the theoretical probability of drawing the blue cube is 10 out of 40. So the same as the fraction in the bag. So is each color equally likely to be chosen? Explain your answer. So seeing everything that we've seen so far, would you expect that all of our colors are equally likely to be chosen? So what you're thinking about here is that, based on our observational data, it doesn't look like they're meant to be equally chosen because we see one at 20% and one at 30%. But when we look down at the theoretical probability, we see that theoretically each of these has a 25% chance. So theoretically, this is equally likely. So is each color equally likely to be chosen? I would say yes. They have the same theoretical probability. And down here at the bottom, we've got one last question using this set of data. It says, how do the theoretical probabilities of choosing the color from exercise 4 compare to the experimental probabilities found in exercise 1? So comparing what we did in 4 to what we did in 1. They aren't exactly the same. They are exactly the same for 2 of them, but they are pretty darn close. And so that's really kind of what our notice should be here, is how do we know they're not perfect, but they're pretty close. And remember, when we're talking about theoretical probabilities and what that means for the real world, it's imperfect, all right? It is an estimate. It is a guess of what it should look like. So they're not perfect, but they are close. So as we flip over to the other side, now we start to use that similar idea. We have an experiment that consists of flipping a nickel and a dime. And the first step is to find the theoretical probability. And so in order to do this, we must find the sample space. So we can see our sample space here is heads, 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 tails, tails, heads, and tails, tails. This is our sample space here. So we're thinking about how many total possible outcomes are there. So if the counts are fair, then the outcomes are equally likely. So the probability of each outcome is 1/4. So the probability of this is one outcome out of 4. This is one outcome out of 4. This is one outcome out of 4, and one outcome out of 4. And so we can see that probability represented down here for each of the possibles. We would say the probability is 1/4. So it's taken a coin where each probability was 1/2, and then it's done the same event twice and made it 1/4. All right. So the probability of 2 heads is 1/4. And so we see that it's got here written that the probability of 2 heads would be 1/4. So again, the way that we figured that out was we found the sample space and we used the total outcomes that we could count from the sample space, and then we found that. So moving over here, it says consider a chance of rolling a number cube? What is the sample space? So we're thinking about all of the possible outcomes. So a regular number cube, six-sided cube, what would be the sample space? Go ahead and write that down. All right, you should be writing that the sample space is 1, 2, 3, 4, 5, or 6. What is the probability of rolling an odd number? So again, our total possible outcomes is 6. Our sample space here is 6. And the probability of rolling an odd number, well, that would be 1, 3, or 5. So that's 3 possibilities that meet the criteria. This is 1/2 or 50%. What is the probability of rolling a number less than 5? So 1, 2, 3, 4 are numbers less than 5. So there are 4 out of 6 possible outcomes, which would be 2/3 or approximately 67%. All right, consider an experiment randomly selecting a word from, or a letter from the word number. All right, well, what is the sample space? Well, the sample space is N, U, M, B, E, or R. What is the probability of selecting a vowel? So our sample space is out of 6. Probability of selecting a vowel, so that's the U or the E, that's 2 out of 6, 1/3 or 33%. Probability of selecting the letter Z, well, the letter Z is not part of our sample space, so that's 0 out of 6 chance, or 0%. Alright, look at the experiment below. Randomly selecting cubes from a bag of 10 cubes. It's kind of got our 10 cubes. It says color the cubes, so the probability of selecting a blue cube is 1/2. Alright, so how many cubes would we need to be in there for this to be out of 10 cubes? The probability would be 1/2. So if we look at this, it tells us, well, for it to be half of them would be blue cubes. So I'm just going to put blue, 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 and blue. So that's 5 blue cubes, and then let's just say the rest of them are red. And finally, we look at this last one. We need to write the sample space for this. So remember, the sample space is compound here. So for our first event, we have a possibility of red or blue. And for our second one, there are 4 different solutions that could come off of each branch here. So we have red, 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 blue, red, green, and red, yellow. And we should start to identify here that it looks like my sample space is going to have 8 different branches. Red, blue, green, and yellow are my possibilities for my second spin. So my outcomes: red, red, blue, red, blue, 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 green, and blue, yellow. So my sample space is going to be out of 8 possibilities here. It says, what is the probability of winning the game? Both spins land on red. So the only instance that meets that criteria is this one up here. And so we see that 1 out of 8, which is 12.5%. All right, please go ahead and flip on over and finish your alone time.